Hi there, I am G. Rohit Kumar. As a part of my Embedded System Internship at Emertxe, I developed a real-time ADAS dashboard using the STM32 Bluepill microcontroller, PICSimLab, and a Python dashboard. The main objective of this project is to demonstrate how embedded systems are used in modern electric vehicles to monitor vehicle parameters, detect potential hazards, and assist the driver using advanced driver assistance system concepts. Instead of using expensive automotive hardware, I developed a complete virtual prototype using PICSimLab. This allowed me to simulate sensors, develop firmware, and visualize data on a Python dashboard. During this presentation, I will explain electric vehicles, ADAS, problem statement, objectives, system architecture, software tools, hardware components, STM32 configuration, firmware design, and finally a live demonstration. So I want to give a brief information about the internship. This project was completed during my embedded system internship at Emertxe. The internship focuses on developing practical embedded engineering skills. During the internship, I learned about embedded C programming, STM32 programming, peripheral interfacing, GPIO, ADC, UART communication, timers, interrupts, debugging, firmware development, real-time programming. The internship followed an industry-level oriented workflow. First, we studied the requirements. Then we designed the firmware. Next, we simulated the hardware. Finally, we tested and validated the system. This project combines everything learned during the internship into one integrated application. Now, introduction to electric vehicles. Electric vehicles are replacing conventional petrol and diesel vehicles. Unlike conventional vehicles, EVs use electric motors powered by batteries. This makes battery monitoring extremely important. Embedded systems continuously monitor battery voltage, battery temperature, motor temperature, current, speed, charging status, driver inputs. Also, if any abnormal condition occurs, the embedded controller immediately alerts the driver. Therefore, embedded systems are considered the brain of electric vehicle. Our project focuses on designing a dashboard capable of monitoring these parameters. Now, introduction to ADAS. ADAS stands for Advanced Driver Assistance System. Its purpose is to improve road safety. ADAS uses sensors to monitor the surroundings of the vehicle. The examples include collision warning, lane departure warning, blind spot detection, parking assistance, emergency braking, adaptive cruise control, etc. In my project, I implemented basic ADAS concepts such as obstacle detection, collision warning, speed monitoring, visual alerts, audio alerts, etc. These are implemented using STM32 firmware. Now, coming to problem statement. Many ADAS systems are expensive. Students usually cannot access automotive ECU. Real vehicle testing is also expensive. Therefore, I designed a low-cost simulation platform. The objectives were develop firmware, simulate sensors, generate live dashboard data, monitor vehicle status, display warnings without requiring a physical vehicle. This makes learning embedded automotive systems much easier. Now coming to project objectives. The first one is acquire sensor data continuously. The second one is process all sensor information inside STM32. And the third one is transmit telemetry using UART. And the fourth one is visualize data on Python dashboard. Fifth one is to generate warnings whenever unsafe conditions occur. And finally, validate everything using PICSimLab simulation. Now coming to system architecture. Now I will explain the system architecture. At the center we have the STM32 Bluepill. It acts as the main controller. Different sensors are connected to STM32. Ultrasonic sensors detect obstacles. Potentiometers simulate accelerator and brake. LEDs indicate warnings, and the buzzer generates audible alerts. all data is processed inside the firmware. Then STM32 sends telemetry through UART. The UART is connected to the computer. Python receives the serial data and dashboard displays the following like vehicle speed, obstacle distance, warnings, vehicle status, bird eye view, real time graph, etc. Thus, the complete system has four layers: hardware layer, firmware layer, simulation layer, and dashboard layer. Now coming to software tools. Several software tools were used. Examples: STM32 Cube IDE. It is used for firmware development. Embedded C, used for application programming. STM32 Hall provides peripheral drivers. And PICSimLab, it provides virtual STM32 hardware. And Python, it is used to develop the dashboard. And PySerial, it is a Python library, it reads UART data. Matplot library, it is a Python library, it also displays graph. And VSP, it creates virtual compounds. And Teratom, it's used to monitor serial communication. Each tool plays a specific role. Now coming to hardware components. The major components used are STM32 Bluepill, ARM Cortex M3 processor, ultrasonic sensors, and it measures the obstacle distance, and potentiometers simulate accelerator and brake pedals. The LEDs visuals warnings, and buzzer used to generate the audio warnings, and the UART transfers telemetry to the dashboard. Since this is a virtual prototype, PICSimLab simulates all these components. Now coming to STM32 configuration. The controller used is STM32F103C8T6. The system clock is 8 MHz. UART speed is 1,15,200 baud. And ADC resolution is 12 bit. Operating voltage is 3.3 volt. Sampling time is approximately 100 milliseconds. And coming to GPIO mapping, PA0 is for accelerator input, PA1 is for brake input, PA3 is for temperature, PA4 is for battery state of charge, and PA5 is for UART-TX, and PA6 is for UART-RX. This means continuously acquire sensor values. Now coming to firmware architecture. The firmware is divided into modules. Main.c, it initializes peripherals. It runs the scheduler and calls all application functions. EVControl.c, it calculates vehicle speed, processes accelerator and brake inputs. ADAS.c, it processes ultrasonic data and it detects nearby obstacles, also generates collision warnings. Fault.c, it checks abnormal conditions, control LEDs and buzzer. UART.c, it formats telemetry, sends serial packets. Ultrasonic.c, it measures distance using pulse timing. This module programming improves maintainability, readability, testing, debugging, scalability, etc. Before going into live demonstration, here are some demo screenshots. The left side is Python dashboard and right side is PICSimLab simulation of sensors. They include ultrasonic sensors, LEDs, buzzers, potentiometers, virtual terminal, etc. Now see, this is STM32 Cube IDE. And here this is the main microcontroller STM32 F103C8TX. So this is the main microcontroller and we can see the pinout view. See, these are the GPIO output pins and these are the USART T1 RX and TX and some input pins, some output pins and ADCs and time pin. Now see, the left side you can see the categories system core, it's a GPIO, and the analog it is a ADC2, ADC1. The timers, time 1, and the connectivity is it is UASART1. Now coming to clock configuration. Here I used the input frequency of 8 megahertz. Okay. Now coming to the Emertxe programming files. See, this is the EV dash, not EV dash, it's main.c. It is the main programming file, and here it connects all the applications. Okay, like I can say that EV control, ultrasonics, ADAS, fault, UART, extra. Okay, see now ADAS.c. See, it is the advanced assistant driver assistant system, and we can see the code here. Now ultrasonic.c, it captures the distances of nearby vehicles and gives out the and sends out the data, transfers the data to UART, and UART it is mainly used for the communication through virtual terminal, etc. See, now EV control.c, and this is also very useful because it shows the torque, motor temperature, battery charge, etc. like that. It also communicates with the main file like emergency braking pedal, etc. like that. And fault.c, during an emergency conditions, this will find the state of the fault and manages the speed, braking systems, etc. Okay. Now going to Python dashboard. Now I am running it. See, this is AVADAS dashboard, and we can see the alarm is none. Okay. The battery percentage is and the battery percentage is see in this the Python dashboard we can see the mode is normal, and here is the speed history, and here is the EV metrics: torque, accelerator, brake, motor temperature, alarm, fault, signal, and this is the ADAS bird eye view. Okay. Now going to PICSimLab. See, here is the spare parts, and this ultrasonic sensor is for front, and it is for left side, and it is for right side of the EV, and it is the LEDs for alarm, and it is a virtual terminal. See, it gives out the data. Now this is the potentiometers. First one is for acceleration, brake, motor control, motor temperature, etc. And the fourth one is like braking system also, and there is the buzzer. Now see, I change the parameters. For first one is the front one. I'm reducing the distance. See what happens in the simulation. See, the bird eye view, it is near to collide. Like see, the distance is decreasing. And wait for a second. See, speed is also increasing. Wait. See now, the alarm is active, and we need to uh, hit the brakes so that we cannot collide the vehicle, nearby vehicles. Okay. See, here is the alarm advisory, the bird eyes view. Now see, I am again changing the distances. Now I am decreasing the left side. Now see the left side is coming to near. So it's like a blind spot. We usually cannot see it. The position is changing. It's coming to near, And here is the also we can observe the speed history. Speed is decreasing and see like that. And now the alarm is none. See, the limit is crossed. Now it is like near to collision. See, the alarm should be none, but see, the speed is decreasing, and it's time for an alarm. Torque is also decreasing. You see, the speed is also decreasing. Now I am decreasing it's to its minimum. Hmm. Now see. Okay. Then. And this is the PICSim spare parts, like this PICSimLab. This is the hardware components I previously explained. Okay. Okay, for now. And finally, thank you.